combination of some things. We're going to talk about two-sided tests. So up until now, we've really only worked with less than or greater than. We're going to talk about how to work with not equal to tests today. We're going to talk about how confidence intervals play a part in hypothesis testing. And we're going to talk a little bit more about type 2 error and a new idea called power. Okay, so the power of a test. So, to start with, let's talk about two-sided tests. Now, when we run a hypothesis test, if we are running a one-sided test, so if our alternative is less than or greater than, so we've established a direction to go if we reject the null. In those instances, the area, the p-value, so the p-value we calculate is associated with the area in only one tail. So if we chose to go less than, so if our alternative was less than, our p-value would be the area associated with that lower tail. So we would have calculated a z-score, we'd have the area to the left. If we were running a hypothesis test where our alternative was greater than, so if we were running a greater than problem, then that means we would have the area in the upper tail. So P would be associated with that area underneath the right tail. Okay? So the tail that we look at is specified by the alternative. Less than means we're looking at the lower tail. Greater than means we're looking at the upper tail. So we're only looking one direction. Okay? Now, if we run a two-sided test. So a two-sided test was when we didn't give a direction to go when we reject. So a two-sided test, the alternative would be that our true proportion is not equal to the hypothesized proportion. So we're not determining greater than or less than. The p-value here then is the probability of getting a sample proportion as far or farther from the null hypothesis in either direction. Okay? So it's saying that if we have a null hypothesis of not equal to, then what's going to happen is we're going to have a z-score. Could be above, could be below. Okay? So we don't know which direction it's going to go, hence the not equal to. Okay? So if it was above, we'd have a z-score here. That means we'd want all of the area to the right. But since we didn't establish a direction, we also then need the negative corresponding z-score and the area to the left. So those two areas together create our p-value. So when you run a test where you're running not equal to as the alternative, you have to account for both tails. Okay? Now, as far as the calculations are concerned, if I was running a one-sided test, if I'm running one of these two up above here, right, we would calculate a certain z-score, and then we'd look it up on the table, or we'd plug it in our calculator to give us our p-value, right? That p-value would be the one tail. If I was doing it for greater than, I would do the same thing. Find the z-score, look it up on the table, or plug it in my calculator, get my corresponding p-value. Now, if I was going to change that, instead of doing less than or greater than, and I wanted to go not equal to, what's the only thing I would change? I'd have to look up either the plus or minus z-score. So I'd do the positive z-score and look at greater than, do the negative z-score and look at less than and put them together, or what would be an even easier way? what do I know about these two areas? They're going to be the same, right? So I can calculate one of them and double it, okay? So when you're running a two-sided test, what you would do is you would look at your z. If z was positive, so if you had a positive z-score, you would look at the upper tail. So you'd run the probability as a greater than. And then once you have that p-value, you would double it to account for the bottom tail as well. On the flip side of that, if you had a z-score that was negative, so that means it's below the mean. So if you had a z-score that was negative, you would find the corresponding p-value and then double it to get the positive. Okay? So the only thing that's really changing as far as mechanics go, everything about the test is the same. You still state your hypotheses, you still check your conditions, you still run through the formula. So calculate z and calculate p. The only difference is once you get p, you double it. Okay? Now, if you were to do this in your calculator, so if you do the same process but you do it in the calculator, you would simply choose the not equal to option, and then the calculator will double that p-value for you. So the calculator, if you run it through that, will do that doubling for you. All you have to do is report the p-value that results. Okay? But if you're running it through the formula, and sometimes you might be required to, once you get to the end of a two-sided test, you have to double whatever p-value you found. Does that make sense? Okay? So that's kind of the big difference between a one-sided and two-sided. Everything else about the mechanics is the same. It's just at the end, find your, or double that value. Okay? So when we find the area, we have to find the area for both tails in our distribution. Okay? Now, confidence intervals, how do they play a role? So when we run a hypothesis test, we have one of two conclusions. We reject the null or we fail to reject the null. If we fail to reject, we're saying that we didn't have enough evidence to get rid of what we're already assuming. So we're not saying that the null is actually true, we're just saying we didn't find anything to say it's false. Okay? When we reject, when we choose to reject the null, we're saying that it's not equal to what we were assuming initially. Our alternative simply tells us then that it's either less than what we originally thought, greater than we originally thought, or not equal to what we originally thought. Now, if we think about that, that doesn't give us a lot of information. If we think back to our basketball player, the basketball player said he shot 80%. When we ran our test, we found that that was probably not true. We found evidence to reject that null. So our alternative was that he shot less than 80%. But then we might wonder, well, what is his actual percentage? So we know it's not 80. We're pretty confident that it's going to be less than 80%, but where is his new average? And that's where confidence intervals can come into play. So if you choose to reject the null, you would want to create a confidence interval to give a set of values that would give us a plausible range of new values. So if it's not what we hypothesized originally, where is that new value? So when we calculate that corresponding confidence interval, we can get an idea of where the new proportion should be. Now, if we run a 95% confidence interval, that would give us an approximate range of new hypothesized values that would not be rejected if we ran a 5% significance level test. So, if we run a two-sided test with an alpha level at 0.05, and we choose to reject the null, that means it's no longer equal to what we said. Then we could create a 95% confidence interval that would give us new plausible values. Where could the new proportion be? And so then we can figure out a range of values that would be plausible for a new null hypothesis. Does that make sense? Now, if we fail to reject the null, then what we said was we don't have convincing evidence that the null is false, which means we don't have anything to say that that's not the center of our distribution. So there's no need for a confidence interval because it's going to tell us the same thing. It's going to say that that could be a center of the distribution. We only need to worry about those confidence intervals when we choose to reject, because then we want to know, well, where might it have moved to? If the center's not here, where could it be? Okay? So, when we want to run confidence intervals, and this will be something that you will be required to do. If you run a test and you reject, they're going to ask you, create a confidence interval to verify. So, because confidence intervals are two-sided, when we think about a confidence interval, we're looking for a middle percentage, right? Which means we have both tails opened up. We're not looking at one direction or the other, we're looking at the middle. So since a confidence interval is two-sided in nature, they correspond directly to two-sided tests. Okay? So what that means is, if I want a confidence interval with a certain confidence level, it would correspond to a two-sided hypothesis test at an alpha level that's the exact complement. So if I wanted a 95% confidence interval, that would correspond to a 5% alpha test. If I ran a hypothesis test at 1%, so if my alpha level was 1%, what would my corresponding confidence interval be, or confidence level? 99. If I ran a test at an alpha level of 10%, what would my corresponding confidence level be? 90. Okay? So one of the things that you want to take from here, if it's a two-sided test, then alpha is equal to 100 minus c. Or c is equal to 100 minus alpha if you just switch the roles there. Okay, so in a two-sided test, alpha is equal to the complement of the confidence level. These are the easy ones, okay, because they correspond directly. If we run a one-sided test, which is most often what we run, we got to take into account the fact that in the test, we're only looking at one tail. In the interval, we have to account for two tails. So, if we have a confidence level that we want to correspond to a one-sided test, our alpha level will be half the complement of our confidence level. Okay, so if we wanted to run a 90% confidence interval, that would correspond to what alpha level if I'm running a one-sided test? 5%. So if I plug 90% in for C, I'm going to get 10% times a half. Alpha would have to be 5%. Okay? Now, the other way of thinking of this, because most oftentimes we run the test first and then we decide to run a confidence interval. So if we're going the opposite direction, if I had an alpha level of 1%, so if my alpha level was 1%, what would my corresponding confidence level have to be? 98. So if alpha is 1%, I would double it to make it 2%, and then that's going to be the complement of my confidence level. So it's kind of like a p-value idea. If we're switching from one tail to two tails, we have to take whatever we initially had and double it to account for both tails. Okay? So when you're doing these types of problems, where you're going to create a confidence interval to go with your test, you need to make sure you pick the correct confidence level with the correct alpha level. If you mismatch them, you might get two alternating claims. Your test might say to reject, but your confidence interval might say you failed to reject. So you have to get them to match up so that they actually say or conclude the same thing. Okay? So be very careful with that when you do those in your problems. All right, then type 2 errors and how they relate to what we call the power of a test. So if we recall, when we talk about type 1 and type 2 errors, a type 1 error happened when we rejected a true null. So the null was true, we decided we had evidence to reject it, and so we did. Well, the probability of making that type 1 error was equal to our alpha level. Since alpha is the threshold, that's where we cut off whether we reject or not, that would give us the probability that we actually commit a type 1 error. Okay? But we never really talked about type 2. So if we know the probability for a type 1 error, we might also be interested in the probability of committing a type 2 error, because we said when we look at the difference between the two, one might be more severe than the other, which is the one we want to limit or try to eliminate. So if the null is false and we reject it, we've made the correct decision. The ability of a test to correctly identify a false null is called the power of the test. So when the null is false and we reject it, that's the correct decision. If we look at the ability of our test to get rid of that false null, we're looking at the power of that particular test. So when you're asked about the power of a test, basically what you need to understand is that it is the ability of the test to detect a false null. Okay? Now, if the null is false and we fail to reject it, that means we've committed a type 2 error. So if power is the ability of the test to correctly detect a false null, and a type 2 error is when we mess that up, then how should type 2 and power be related? Okay. This should be the complements. Okay? The power is the probability that we detect the false null, the probability that the test will be successful. Type 2 is the probability that we don't detect the false null. Now, since we tell type 1 the probability is our alpha level, we call the probability of a type 2 error beta. Now, we'll never actually make you calculate beta on its own. The main thing you have to understand here is that when you look at the power of a test, power and beta are complements of each other. So if they tell you the power of a test is 75%, so essentially 75% of the time the test will correctly identify the false null, then the probability that you would commit a type 2 error while running that test would then be 25%. Okay? Or they could work it in the opposite direction. If they tell you that you have a 5% chance of creating a type 2 error, that means the power of the test would be 95%. Okay? So you're never going to have to calculate power or calculate beta on its own, but you do need to know how they relate. Okay? So you need to know that power and beta go hand in hand. So beta is the type 2 error. It's the complement of the power of the test. Okay with that? All right, so we kind of discussed this. You don't have to write this down because we discussed this when we first talked about type 1 and type 2. I just want to reiterate kind of the ideas here. So when we want to reduce type 1 errors, if those are the errors we want to avoid, we simply need to reduce alpha. Okay, so if we reduce our alpha level, we reduce type 1. But if we reduce type 1, that means we're failing to reject more often. We're going to start making more type 2. When one goes down, the other goes up. Okay? If we want to reduce type 2 errors, then we need to increase alpha. Increasing alpha leads to more rejections, and more rejections means less type 2 errors. So this means we're going to we'll reject more often and therefore create more type 1 errors. And then we discuss, well, maybe we want to reduce both. So maybe we're not okay committing either error. We want to make those as small as possible. What's the only way to do that? Increase your sample size. Okay? So if you absolutely have to try to reduce both, take whatever your original sample was and increase it. The bigger the sample, the lower both types of errors will happen. Okay. So, here are the problems I want you to try out.